Hello, I'm Margarita Caulfield, and this is my submission for ME 3210's Project 3, submitted to Dr. Hasson Rashidi for the fall 2024 semester. Hi, today I'll be covering 5 essential techniques in design and manufacturing: metal rolling, lathe operations, deburring, chemical machining, and water jet machining. Each of these techniques contribute significantly to creating, refining, and finishing materials across industries like aerospace, automotive, and electronics. My goal is to walk you through each technique's application, why I think it's important, its capabilities, and its limitations. First up is metal rolling. Metal rolling involves passing metal stock through one or more pairs of rolls to reduce thickness, make it uniform, or shape it. Rolling can be hot or cold. Hot rolling happens at high temperatures, making the metal more malleable and ideal for breaking down large blocks of metal into basic shapes. Cold rolling is done at room temperature and improves the metal's strength, surface finish, and dimensional accuracy. Applications for metal rolling are broad, and it's used for making sheets and coils for car bodies, appliance casings, building materials, and pipes. Cold rolled steel is particularly valuable in automotive and appliance industries, where precision and smoothness are essential. Metal rolling enables mass production of metal parts with a high degree of precision, which is fundamental in industries that need reliable, consistent parts. It's cost-effective on a large scale and enhances the metal's structural properties, making it useful in industries where durability is key. Rolling can produce large quantities of uniform metal parts quickly and with high accuracy. The smooth, polished finish achieved through cold rolling eliminates the need for extensive secondary processing. The process can handle various metals, including steel, aluminum, and copper, adapting to the needs of different industries. Additionally, it can create metals with enhanced stress and fatigue resistance due to strain hardening. Metal rolling has some limitations, primarily its high equipment and setup costs. Rolling mills are massive, require some significant infrastructure, and the machinery is expensive to maintain. This technique also mainly produces flat or cylindrical shapes, so it's less suitable for creating complex geometries. Rolling also introduces internal stresses that, if not controlled, can warp the material. This makes it necessary to carefully monitor and control the process, adding further cost and complexity. Now, let's discuss the lathe machine. A lathe is a versatile tool that rotates a workpiece around a central axis, allowing the operator to perform various operations such as cutting, sanding, drilling, and threading. Lathes are widely used to create symmetrical objects like screws, pipes, and pulleys, making them invaluable in industries like automotive, aerospace, and even furniture making. The lathe is often called the mother of machining tools because of its importance in manufacturing. Lathes are essential for producing precision parts with complex shapes and high dimensional accuracy. The ability to shape materials with such accuracy is crucial for components in engines, medical devices, and even instruments that require perfect symmetry and smooth surfaces. One of the most valuable aspects of lathes is their versatility. They can be used on a variety of material, including metals, woods, and plastics. CNC, computer numerical control lathes, bring even more precision and automation, allowing complex, custom designs to be programmed and machined with minimal human intervention. This makes lathes suitable for high volume production as well as custom one-off parts. Lathes can be equipped with additional attachments for drilling, grinding, and milling, adding to their multifunctionality. Despite their versatility, lathes are limited in that they are most efficient for creating cylindrical or symmetrical objects. Parts with irregular shapes require different machining techniques. While CNC lathes enhance productivity, they can be costly to set up and maintain, and programming complex parts requires specialized knowledge. Additionally, lathes create a significant amount of waste material, which can be costly to manage and challenging to recycle, particularly with soft materials like aluminum. Now let's talk about deburring. After machining or shaping, many parts have rough edges, sharp points, or small metal fragments called burrs. Deburring is the process of removing these imperfections to create a smooth, safe finish. It can be done manually using tools like files or rotary brushes, or with machines that automate the smoothing process. Deburring is crucial for safety, functionality, and aesthetics. Rough edges can cause injuries or wear down moving parts and machinery. Additionally, a smooth finish is essential for parts that must fit precisely together, like in engines or electronics. In many cases, deburring is also part of quality control, ensuring that products are safe and visually appealing. Deburring greatly improves the overall quality and safety of a product. For intricate parts, manual deburring is an option, though it's labor-intensive. For larger production runs, automated systems can quickly and consistently remove burrs, significantly speeding up the finishing process. In industries like aerospace and medical devices, deburring is essential to ensure parts function correctly and without interference, as even tiny imperfections can disrupt performance. Manually deburring is labor-intensive and time-consuming, making it impractical for high-volume production. Automated deburring systems, on the other hand, are expensive and may struggle with complex or delicate parts that require fine detailing. Some materials, especially metals like aluminum, are prone to developing burrs again due to their softness, which may require repeated deburring processes and add to the production cost. Now, onto chemical machining. Unlike mechanical machining, this process uses controlled chemical reactions to remove materials from a workpiece. The part is masked with a protective coating, leaving only specific areas exposed to the chemical etchant. It's a non-traditional machining process that is typically useful for producing complex, thin, or delicate parts that could be damaged by traditional tools. Chemical machining allows for the precise removal of material without introducing mechanical stress. It's perfect for applications where even small inaccuracies could be disastrous, such as in aerospace, electronics, or medical devices. For example, it's used to create intricate components for electric circuits and high-strength parts for aircraft. It's especially effective on aluminum and titanium. This process can be highly precise and intricate parts that would be difficult to machine using conventional methods. It's effective for materials that are hard to cut, like titanium or certain stainless steels. Chemical machining also provides smooth finishes, minimizing the need for additional processing. It's ideal for making lightweight parts with complex patterns, such as thin metal meshes or intricate heat exchangers. Chemical machining's primary drawbacks are environmental and cost related. The chemicals used are hazardous and require careful handling and disposal, which can be costly. Additionally, the process is relatively slow compared to mechanical machining and is best suited for thin materials. Thick parts take much longer to etch, reducing efficiency. The need for masking and etching control also makes it labor intensive, increasing both time and cost. The last technique I'll discuss is water jet machining. This process involves a high-pressure jet of water, sometimes mixed with abrasive particles, to cut through a wide range of materials. The water jet's speed and pressure create precise cuts that don't produce heat, so it's suitable for materials that are heat sensitive. Water jet machining is highly versatile and can cut almost any material, from steel and ceramics to softer materials like rubber and foam. Its ability to create intricate, precise cuts without heat makes it invaluable for sensitive materials that might warp or weaken under traditional cutting methods. Water jet machining allows for high precision with cuts often within 0.001 inches. It's known for leaving a smooth finish, often eliminating the need for secondary processes. Water jets can cut complex shapes, making them ideal for custom or artistic applications as well as industrial uses. They also produce no heat effective zone, preserving material properties and preventing thermal distortion. However, water jet systems are and expensive to purchase and maintain due to high pressures required. They can also be slower than some mechanical methods, especially when cutting very thick or hard materials. The abrasive particles used in some water jet systems create slurry waste, which requires disposal and can be environmentally challenging. Finally, while water jets can cut most materials, there are limits to thickness and hardness, and thicker materials may lead to accuracy issues on deeper cuts. In conclusion, each of these 5 techniques, metal rolling, lathe operations, deburring, chemical machining, and water jet machining, plays a crucial role in manufacturing. They each contribute to shaping, finishing, or refining materials to meet the precise needs of different industries. Whether it's high efficiency of metal rolling or the versatility of water jet machining, Understanding the capabilities and limitations of these methods is essential for quality design and production. Thank you for listening. And here I've attached my works cited.